So this one is January 2023, Unit 6. So what actually happened in acid, like potassium manganate, Mn7 is there, it will turn into Mn2. So the reduction happened for Mn7, it will turn into Mn2. But if we don't acidify, then what will happen? The complete reduction will not occur for the manganate 7 ion. Or it will, like it is by itself, it is reduced, so it acts like an oxidizing agent here. Or if we have not acidified solution, so Mn does not reduce to +2, it might reduce to +4. That is also a reason for that. So both reasons are acceptable, like does not reduce completely to +2 or changes to Mn7 changes to +4. Neither hydrochloric acid nor nitric acid can be used for this titration. Give a reason why it cannot be used. So whenever like we are doing that this titration, we don't use the nitric acid or the hydrochloric acid. So what might be the reason for that? If you use a hydrochloric acid H plus and Cl minus. So as a result, what will happen? Because it is reacting with Mn plus 7, so it will produce Mn plus 2. This will be reduced and the chloride ion will be oxidized. So why hydrochloric acid is not used? Otherwise, the chloride ion will be oxidized and it will form a chlorine molecule. And why this reason is written in the book as well. Why nitric acid is not used, like a nitrate ion is there. These nitrate ions can also react with iron 2 ion and it can form iron 3 ion. So the iron 2 in the solution can turn into iron 3. That's why nitric acid is not used. And hydrochloric acid, the chloride ion in hydrochloric acid may be oxidized. That's also a reason. So these two reasons are given in the titration topic, that why these two acids are not used for iodine and this potassium manganate and iron 2 titration. Ionic half equation: calculate the percentage by mass of iron 2 in the sample of a lone sand. So first, we should know the complete equation for a reaction between them, like the mole ratio. This will multiply by 5 because the number of electrons should be same. So it means the ratio for Mn plus 7 to iron plus 2 is 1:5. So we have the titration, mean titer is there. So we have the mean titer and we have the concentration. So first we'll find the concentration of Mn plus 7. And then this Mn plus 7. Then from this Mn plus 7, we'll work out the moles of iron 2. And these are the moles in 250 cm cube. You'll work out the mass, how much mass, because in the question, we make a solution like 4 gram is there, 250 cm cube, and the sample was shaken with 50 cm cube of hydrochloric acid, and the resultant mixture, the full was titrated. So we use a complete mixture for titration. After getting a moles of iron 2, multiply by the molar mass, we'll get the mass in gram and compare, because we need a percentage. The total mass of a lawn sand is 4.5 grams. So first the moles of MnO4, because the ratio of potassium manganate and MnO is 1:1, so it will give the same. So concentration into volume, concentration is 0.02 and the volume is 40.35, and this will be divided by 1000. So this will be 0.0008 moles will be there. And then the ratio is 1:5 for iron 2. So moles of iron 2 will be 5 times the moles. So 0.0008. We multiply by 5, so it will be 0.00. 4 will be there. And after getting the moles of iron 2, what about the mass of iron 2? These are the moles. The mass of Fe plus 2 will be moles multiplied by the molar mass 0.004 multiplied by the molar mass of iron is 55.8 or 56. So you can multiply, you get the mass in grams 0.22 grams. Now the percentage of iron to mass of iron to 0.225 divided by mass of a compound 4.5 into 100. So this will be about 5% we have. So about 5% of this sample contain iron to iron. The titration is carried out using an apparatus as shown, a burette containing potassium manganate, a conical flask. At the end point of a solution changes to permanent pale pink. To repeat experiment, burette is refilled with potassium manganate and the procedure carried out again. Give 3 ways in which titration carried out to give a most accurate possible burette reading. Assume the equipment is same, the burette is clamped vertically, the titer volume are read at eye level. So what are the other improvements we should do? First thing, we should use a white background or a white tile. You can also mention that. And then when we are adding the potassium manganate from the burette, we should also always swell the mixture or shake the mixture. That is also one thing. And when we are adding this potassium manganate, we should add it drop wise near the endpoints. That is also another thing which we should do. These are the improvements which you have to mention. Like using a white background, white tile, or adding near the endpoint, adding drops from the burette, like slowly adding from the burette, and swirling the mixture. When the reagents are mixed, you should swirl the mixture. Wash burette with potassium manganate solution. They already mentioned that it is washed with potassium manganate here. Burette is refilled. Burette is refilled with potassium manganate. So if you wash with potassium manganate, it's the same thing if you refill. You can mention wash the conical flask with distilled water and then wash it with, or you can mention if you want to improve, wash the burette with a distilled water and then wash with the potassium manganate solution. That you can mention. In question 4, the compound 2 ethoxy ethonyl aminobenzoic acid can be prepared by reaction of 2 aminobenzoic acid with ethonyl chloride. So you can see here this one. So one of the hydrogen is replaced and this link is added here. The procedure, 5 grams of 2-amino-benzoic acid and a few anti-bumping granules. What is the purpose of anti-bumping granules? To make sure that it is like the bubble does not form a large size or a uniform boiling happen. 100 cm cube of a pear shape fit in a reflux condenser. 10 cm cube of ethonyl chloride by pouring it slowly down into a condenser. Then bring the mixture to the boiling and heat under reflux for 15 minutes. Usually heating for longer period of a time is to make sure that all of the mixture, like they mix completely with each other. Allow the mixture to cool and slowly add 10 cm cube of water. Heat the solution until boils and allow the solution to cool to room temperature. Collect the crystals by filtration under a reduced pressure, so Buchner funnel, and recrystallization of the impure product from a mixture containing equal volume. Give two reasons why it is often necessary to heat reaction mixture under reflux in step 3. So what usually happen when two substances, like it's like activation energy might be higher for them. So we want to make sure that they react completely. So mainly the reason is that so they completely react with each other, and the two reasons why often necessary heat under reflux. So second thing, why under reflux? One is like heating it so that they mix thoroughly, like the reaction is slow, and the another vertical reflux condenser is there, so it prevent the reaction mixture to escape. Otherwise, what might happen? The reaction mixture might escape, and that's why the vertical condenser is used or a reflux condenser. Explain why in step 4 water is added slowly uh, to the cooled solution. So why gradually the water is added? Why small quantity of water is added? Because some of the reactions are exothermic, like sulfuric acid with water. It's highly exothermic reaction. So same thing when ethanyl chloride is already there, which is in excess. So if you add a water, that will also that is also exothermic reaction. So exothermic reaction is there between the ethanyl chloride and the water, or highly vigorous reaction, you can also say. And second thing, that because of this vigorous reaction, what might happen? The substance might escape, or it is also releasing HCl. HCl is there, even in the complete reaction, HCl is there. But the main reason for heating it, like adding it small amount, like water slowly, is the exothermic reaction between ethanyl chloride and water, or vigorous reaction, which may result in an increase in temperature of the container, or may the substance, the volatile liquids might escape. Because if a temperature increase too much, the liquids, the volatile liquids, liquid with a low boiling point, start to boil up. Draw a label diagram of apparatus used for, so you have to show step. It is a filtration under reduced pressure. So side arm is to the pump, and at the top we have the filter paper here. And there's also advantage of using a smaller passage for the funnel. Like example, if a funnel is there with a smaller passage, then this will filtration will be quicker as compared to a long passage, because long passage there will be greater adhesive forces between the glass and the liquid. That's why it will take a relatively longer time. And whenever you draw the label diagram, like label all the points. The melting temperature can be used to confirm the identity, draw label. So melting point apparatus, look, I'll explain how melting point, how to work out the melting point. So we take a capillary tube. Capillary tube is a very thin, narrow tube made up of glass. First, it's a capillary tube which is open from both ends. First, what we close this one of the end. How we close one of the end? So we place over the place this capillary tube over the Bunsen burner until it become red hot. When it become red hot, we tap the part which is hot. We tap on the any hard or a rigid surface. We tap. So when we tap, then this capillary tube will be closed, because the glass, that part become melted, like red hot, it can be deformed. So then we tap on the uh, time to time we tap on the solid surface, any rigid surface. So this will close this end. Then we add, in this one we add a solid which we want to determine its melting point. So we add a solid now. Then this solid, which is like we want to determine the melting point of this solid. Then we take a container. Usually the melting point apparatus is this, how the melting point apparatus looks like. That is to make like convection current. That's the reason why the side arm is there, filled with a liquid which is having a temperature, boiling temperature more than the melting point of a solid, which we are finding. Otherwise, the temperature will not rise. We place a thermometer, and the characteristic of this liquid, it should have a high boiling point than the substance which melting point we are determining, finding, and as well as it should be a clear liquid because it should be see-through. And using a rubber band, a capillary tube, we place a capillary tube. The capillary tube which we close one end of a capillary tube, we place, and using a rubber band, we stick to this. And there's a solid inside here, which is visible. Then we supply the heat energy. So whenever you draw a label diagram. So capillary tube with a sample is there. This is the stopper, like just to make sure that it will boil off. And thermometer is also placed. Now, when we supply the heat energy, the moment we observe that the solids start to melt, we'll read the thermometer, record the value of reading on the thermometer, and that will be the melting point. That's how it is done. So sometimes they ask like how capillary tube should be closed. So you will place on the, because both ends of a capillary tube are open. So place on the hottest part of the flame on the Bunsen burner until it become red hot, and then tap on the rigid surface until the one end is closed. Said how this melting temperature determination show that pure sample of 2-ethonyl aminobenzoic acid has been prepared. So how we can identify, because if it's a pure sample, it will have a smaller range will be there, or you can also say a sharp melting point, and its melting point should match with a standard value. If it is a pure, like standard value is there. So whenever, if we say water is pure, so pure water, how we know it's pure? So pure water has a boiling point of 100. That's a standard value. So it should match with the standard value, and it should have a small range or a sharp melting point. Even though when we have a sample, because in the lab we don't get 100% pure, that's why we don't get a sharp value. We always get a range, but that will be smaller range. So by calculation that in a preparation of 10 cm cube of ethynyl chloride in excess compared to 5 gram of, so by calculation in preparation 10 cm cube of ethynyl chloride is in excess compared to 5 gram of 2-aminobenzoic acid. So just work out the moles of each and then compare the moles. So the first one for moles of 2-aminobenzoic acid, moles equal mass in gram over molar mass. So molar mass of is 137. So this will be 0.036. And moles of ethonyl chloride. First, we should know the mass. We have the volume. And the density is 1.1. So density is mass over volume. So mass is density multiplied by volume. So 1.1 multiplied by volume 10. And then divided by the molar mass, because we need the moles. So it will be 11. So then 11 divided by 78.5, that will give us the moles of ethonyl chloride, which is 0.14. So 0.14 and 0. So the ratio between them is 1:1 according to equation. But here for 2-amino benzoic acid, it's only 0.01 compared to the ethonyl chloride. So which shows ethonyl chloride is in excess, like more than what we need. Student carried out the preparation using using amounts of reagent given in E. So student and obtain a yield of 56.7. Calculate the mass of ethonyl 2-ethonyl amino benzoic acid obtained. So first we'll use a ratio like we have the formula moles, the percentage yield. The percentage yield is what? Percentage yield is a practical value divided by theoretical value into 100. So the percentage yield is only 56.7. So we have this 56.7. And the amount of the product which we obtain, that will be the practical value which we need. Theoretical value we can work out from the limiting reagent, limiting factor. Like we worked out the moles of the limiting factor, which was 2-amino benzoic acid. And what is the ratio between 2-amino benzoic acid and the product? The ratio is likely to be 1:1. So this is a limiting factor because we use the moles of limiting factor to get the product. So how many moles we calculated in the last part? That was 0.036. So if you were having 0.036, so 0.036 moles of a product will be there. And then this moles of a product multiplied by the molar mass to get the mass in gram. And that will be the theoretical value. How to work out the molar mass? That is the question. There are two different ways you can work out the molar mass. Look, we know the molar mass of 2-amino benzoic acid that is given in the question. And we know the moles of ethonyl, mass of ethonyl, molar mass of like 78.5 and 137. So this was 137 and this is 78.5. And moles of HCl, like the molar mass of HCl according to equation, chlorine is 35.5, hydrogen is 1, so 36.5. So if I add these two and subtract the mass of HCl according to the equation, if it, for example, if it was 2 was written here, then I'll multiply this by 2, but nothing is written, so we don't multiply. So if I subtract them, I will get the mass of this compound. So we'll multiply by the molar mass of this compound, we'll get the mass in gram, and then simply use a percentage yield as a practical value, divide by theoretical value into 100. Percentage yield is given, theoretical value is there, so you can work out the practical value. So this was the last part of the question.